Welcome to our quantum deep dive.
Glad to be here.
Today we're diving into something pretty fascinating. Sits right at the crossroads of fundamental physics and, well, potentially game-changing tech.
Multiferroic materials.
Exactly. And their role in the quantum future. We're drawing heavily from an essay by Jürgen Schneeppert, Multiferroic Materialien, Zukunft der Quantentechnologie.
Yeah, it's a great piece. And these materials, they're remarkable because they can juggle multiple ferroic orders at the same time. Think of it like a Swiss Army knife, but for materials science.
Okay, so more than one trick up their sleeve.
They can be ferroelectric, meaning they have this inherent electrical polarization you can flip with an electric field.
Right.
And ferromagnetic, so they have their own internal magnetism. And some are even ferroelastic, which means you can deform them and they stay that way.
So materials doing several things at once. Schneeppert points out that's actually pretty rare, right? Because the conditions for one property often rule out the others.
That's exactly it. It's like finding an animal that can both fly and live deep underwater. Nature doesn't usually combine those things easily.
Right.
And here's where it gets really compelling. Within these multiferroics, these different orders can actually talk to each other. They're coupled.
Coupled? How so?
It means one property can influence the other. This opens up totally new functions you just don't get otherwise. The classic example is magneto-electric coupling.
Oh, right.
Imagine being able to control the material's magnetism just by applying an electric field, or doing the reverse affecting its electrical state with magnetism.
Whoa, okay. So instead of needing a constant electric current to make a magnetic field, like an electromagnet, maybe just a quick zap of voltage could flip its magnetic state.
You got it. And that sounds like it could slash power consumption, doesn't it? Especially in things like computer memory. And Schneeppert really highlights this. Huge potential across loads of technologies, more energy efficient memory, but also incredibly sensitive sensors, new types of actuators, and crucially for us today, potentially energy saving quantum tech.
It feels revolutionary. But this field didn't just appear yesterday, did it? There's a history here.
Oh, absolutely. The first sort of hints started back in the 1950s. Researchers saw early signs of these magneto-electric effects in certain oxides. But a really key moment was 1959. J. figured out the theoretical rules based on crystal symmetry that a material needs to have for this coupling to even be possible.
So theory first, laying the groundwork.
Yeah. And then Astrov and others quickly followed up with experiments that actually proved it worked. They confirmed the effect.
Theory predicts, experiment confirms. Love it when science works like that.
But then things came really interesting again. In the 2000s, there was this big resurgence. Mostly because of huge leaps in material science and nanotechnology. We just got much better at making and studying materials really, really precisely. People like Spalding and Fiebig were key figures here.
Right.
They really dug into how these couplings worked at the atomic level and figured out ways to actually design and synthesize new multiferroics on purpose.
And Schneeppert mentions specific materials from that time. Bife and TBM anaerobes. Why were they so important? Bismuth ferrite and terbium manganite.
Yeah, those became sort of the poster children for a while. They showed really strong coupling effects, strong interactions between their electric and magnetic sides.
So good test cases.
Exactly. Perfect model systems to really understand the fundamental physics and start thinking about, actual applications.
Okay, so we have these materials, multiple orders, coupling. Why should someone tuning in, maybe interested in future tech, really pay attention?
Well, if you think about the big challenges in electronics right now, miniaturization, making things smaller, energy efficiency, using less power, multifunctionality, getting more features in one device. Multiferroics offer potential answers to all of these. Seriously.
Schneeppert specifically mentions data storage. How could they change, say, the memory in our computers or phones?
Well, that magneto-electric effect we talked about, controlling magnetic bits with electric fields, that's the dream for magneto-electric RAM.
MRAM, okay.
Could be way faster and use much less energy than current tech. Because, generally speaking, flicking an electric field takes less power than pushing current around to generate magnetic fields.
That sounds like a recipe for much longer battery life.
Yeah.
What else? Sensors.
Definitely. Their sensitivity to both electric and magnetic fields makes them amazing candidates for new sensors. Think detecting incredibly faint magnetic fields for medical imaging, like MEG, or maybe super precise navigation systems.
And actuators, like tiny motors.
Yeah, using their ability to change shape in response to fields, you could get really precise control for micro machines or robotics.
Fascinating. and the quantum connection. Where do they fit in the quantum computing puzzle?
Now that's a really interesting angle Schnepp brings up. The potential is there to use them to build qubits.
The building blocks of quantum computers. How?
Well, the different stable states in the material, maybe the direction of electric polarization or magnetic alignment could represent the 0 and 1 of a qubit. And the key thing is you might be able to control these quantum states using electric fields, which could be very low power.
So potentially stable qubits that are easy to control electrically.
That's the hope. It's still early days for this application, but it's a very active area of research.
So potential for next-gen computers too.
Right. And Schnepp also points out, just studying these weird materials pushes our basic understanding of physics and chemistry forward. It drives materials science innovation generally.
Okay, let's get into the nitty-gritty a bit. These ferroic orders. Can you break them down for us? What is ferroelectricity again?
Sure. So ferroelectricity. At its core, it's about a material having a spontaneous electric polarization. Imagine the positive and negative charges inside the material are naturally slightly separated, creating an internal electric dipole moment, an electric field.
Okay, it has a built-in polarity.
Exactly. And the crucial part is you can reverse this polarity by applying an external electric field. Schnepp includes the formula P, we'll call it P, by E20 by 820 by 91 plus 1E, but the key takeaway is that P, the polarization, stays even when you turn E, the external field, off. It remembers its state.
Like a tiny electric switch inside the material. Got it. And ferromagnetism. We know magnets, but what's the physics?
Ferromagnetism is similar, but with magnetism. It's a spontaneous alignment of the tiny magnetic moments of the atoms to their spins. This alignment comes from quantum mechanics, specifically the exchange interaction. So the material has a net magnetization, M, even without an external magnetic field, H. Think of your fridge magnet, that's ferromagnetism in action. The relation is M equals 0 by E20 by 820 by 98H. But again, the key is that M exists when H is 0.
A permanent internal magnetic alignment. Makes sense. And the last one, ferroelasticity. That sounds different.
It is a bit. It's about mechanics. A ferroelastic material can be deformed by stress, like bending it, and it will actually hold that new shape after you remove the stress.
Really? It just stays bent?
Yep. It happens because the material's crystal structure can exist in different stable arrangements or domains. Applying stress can flip the material between these domain states.
Wild. So many ways for these materials to be ordered. Now, Schnepp stresses the role of symmetry. How does that fit in?
Symmetry is absolutely fundamental. The specific arrangement of atoms in the crystal lattice, the crystal structure, and its inherent symmetries dictate everything. Many multiferroics have the structure called a perovskite.
Perovskite. I've heard that name before.
Yeah, it pops up a lot in material science. It's a specific atomic arrangement that turns out to be unusually good at allowing these ferroic orders, especially electricity and magnetism, to coexist. Schnepp mentions the space group symmetry. That's like the complete description of all the symmetry operations you can do to the crystal and have it look the same.
Okay, space group symmetry.
Yeah.
Sounds complex. But basically, the atom layout sets the rules.
Pretty much. Think of it like this. The structure needs to allow certain kinds of distortions or alignments. For ferroelectricity, the crystal structure must lack what's called an inversion center. It needs to be non-centrosymmetric. That lack of symmetry allows the positive and negative charges to separate spontaneously.
Okay.
For ferromagnetism, the atomic arrangement and electron interactions need to favor that parallel spin alignment we talked about. The space group tells you which of these fundamental symmetries are broken or preserved in the material.
And the coupling between orders, like magnetism and electricity working together, that's also down to symmetry?
Exactly. Schnepp explains these orders arise from symmetry breaking. Ferroelectricity breaks inversion symmetry. Ferromagnetism breaks time reversal symmetry. For them to couple, the underlying crystal symmetry has to be low enough, basically, to allow both types of symmetry breaking to happen and, crucially, to influence each other.
Got it. The basic architecture has to be just right. So let's talk about those couplings. Magneto-electric coupling.
Right, the link between electricity and magnetism. Schnepp gives the relationship Oxb 10 am blue 50 by A5, Ajir by A10, Oxb 50 by A5. That alpha is the magneto-electric tensor. It tells you how strongly a magnetic field H can induce an electric polarization, P, or vice versa.
So applying a magnetic field literally makes the charges inside shift.
In simple terms, yes. And in some materials, applying an electric field can change the magnetization. That two-way street is the exciting part. Chromium oxide, chrompiero, is a classic example used in some sensitive magnetic field sensors.
Okay, and elastic coupling. How does stress come into it?
That's about how mechanical forces affect the ferroic properties. Piezoelectricity is a prime example, which Schneepat mentions. You squeeze or stretch the material, apply stress, and it generates an electric voltage or polarization. Piezo by Liney by A2 by 87, by Z2 by 8050, by A20 by A20, by A20 by 87, by E10 by A10 by 87, by A10 by B50 by A5.
Like in a gaslighter igniter.
Exactly like that, or the reverse. Apply a voltage, and the material changes shape. That's how piezoelectric actuators work, giving really precise movements.
So you can squeeze it to get electricity or use electricity to make it move. It's all deeply connected. Now, Schneepat divides these materials into types. What are the main categories?
He focuses mainly on two broad types, intrinsic and composite multiferroics.
Okay, intrinsic first.
Intrinsic means the multiple ferroic orders, like ferroelectricity and magnetism, arise naturally within a single material from its own crystal structure and electrons. The coupling is built in, a consequence of its fundamental symmetry.
And biferrate, bismuth ferrite, is one of those. How does it work?
In Befeo, the ferroelectricity comes from the way the bismuth ions and their electrons sit in the perovskite structure they cause a distortion. The magnetism, specifically antiferromagnetism, where spins align oppositely, comes from the iron ions.
Okay.
And Schneepat mentions the Jalashinsky-Moria interaction. It's a subtle magnetic effect that sort of twists the spin slightly, and this twist is crucial for linking the magnetism to the electric polarization.
A twist that connects them.
Cool.
And the other example, TBMNO, terbium manganite.
That one's fascinating. It has this complex spiral arrangement of magnetic spins, and it turns out the specific magnetic spiral structure actually breaks the crystal symmetry in just the right way to induce ferroelectricity.
So the magnetism causes the ferroelectricity.
In that case, yes. It's a really elegant example of how orders can be interconnected through symmetry.
Schneepat also mentioned hexagonal ferrites, like YMNOs.
Right, they have a different crystal structure, hexagonal layers. But they also combine ferroelectricity and magnetism, often influenced by how these layers interact.
So intrinsic materials have it all in one package. What about composites?
Composites are engineered. You basically take two different materials, one that's, say, ferroelectric and another that's ferromagnetic, and physically combine them.
Like mixing them together?
Yeah, or layering them. The idea is to create a hybrid system where the properties of the individual parts are coupled through their physical interface or proximity.
How do you actually make them?
Schneepat describes a few ways. You can make layer composites, thin films of a ferroelectric, like battio, grown on a ferromagnet like knife. The interface between them is key.
Okay.
Or particle composites embedding tiny ferromagnetic particles, maybe COFIO, inside a ferroelectric matrix like PZT. The close contact allows them to interact.
Like embedding chocolate chips in cookie dough, but functional.
Kind of. And then there are ceramic composites made by mixing powders of the different materials, say bithio and battio, and then sintering them together at high temperature.
So building the material piece by piece, what's the advantage of doing that?
Flexibility. You can pick and choose materials with strong individual properties and combine them. It gives you more design freedom. Plus, you might be able to use established, cheaper methods to make the components.
Sounds good, but there must be downsides.
No, absolutely. The interface between the materials is critical, but it can also cause problems like energy loss, reducing the coupling strength. Making those interfaces perfect is really hard.
Right.
And long-term stability can be an issue too. Will the two materials react or degrade over time where they meet?
So trade-offs between intrinsic and composite. Does Schneepat mention any general difficulties in the field?
He does. Classifying them neatly is tricky because the mechanisms are so varied. Sometimes a material might act intrinsic under some conditions, composite-like under others, and there are big fundamental challenges. Those strict symmetry rules limit the number of good intrinsic candidates. Crystal defects are a huge problem. They mess up the properties. Many aren't stable at high temperatures or under stress.
And making them usable.
Yeah, technological hurdles. Scaling up production reliably and cheaply is tough. Integrating these often sensitive materials into existing manufacturing processes is hard, and often the actual coupling effect, while present, just isn't strong enough yet for many applications.
Lots of work still to do. So how do researchers actually make and study these in the lab? Synthesis.
Schneepat covers the key techniques. For thin films, which are vital for electronics, you need amazing control. Pulsed laser deposition, PLD, uses a laser to blast material from a target onto a substrate.
Okay.
Molecular beam epitaxy, MBE, is even more precise, grows films literally atom layer by atom layer in ultra-high vacuum, very high quality, but slow and expensive.
Right.
Chemical vapor deposition, CVD, uses gas phase reactions to deposit films, often better for larger areas.
Sounds very high-tech.
Yeah.
Any simpler methods?
Yeah, sol gel is a chemical route. You start with a liquid solution, make a gel, then heat it. It's good for some complex oxides like BIFO, potentially cheaper and scalable. And then there's classic solid-state synthesis mix powders. Press them, bake them at high temperature. Simple, good for bulk amounts, but you get less control over the fine structure and potentially more defects.
So different tools for different jobs. Once you've made something, how do you know what you've got? Characterization.
Essential. X-ray diffraction, XRD, is the workhorse for figuring out the crystal structure. Tells you what phases are present, how well ordered it is, looks for strain. Based on Bragg's law, no excesses tenkoisim.
Okay, checks the atomic arrangement.
Then for magnetism, suck-wide magnetometry is incredibly sensitive. Measures the magnetic moment, how it changes with temperature or field, lets you probe the magnetic order and magnetoelectric coupling.
Squay-deep, super sensitive.
Yeah, superconducting quantum interference device. And Raman spectroscopy is great too. It shines laser light and looks at how the light scatters off the vibrations of the atoms, the phonons.
Phonons, okay.
Those vibrations are very sensitive to the crystal structure and symmetry. So Raman can tell you about phase transitions, defects, and how the lattice is involved in the ferroic orders.
Sounds like you need a whole toolkit to really understand these materials. Shnepat mentioned defects being a problem. How do they mess things up?
Big time. Defects, missing atoms, extra atoms, misaligned crystal grains can pop up during synthesis if conditions aren't perfect.
Right.
They can kill the ferroelectric polarization, weaken the magnetism, create leakage paths for current, and really disrupt that crucial coupling between the orders. Minimizing defects is a constant battle.
Getting that perfect crystal is key. Okay, after all that groundwork, let's swing back to the applications Shnepat is excited about. Memory.
Yeah, huge potential there. Magnetoelectric memories using voltage to write magnetic bits. Remember, M equals AE. Super energy efficient.
Right.
And ferroelectric RAM, FERRAM, using the ferroelectric polarization itself to store data. It's non-volatile, low power, lasts a long time. Challenges are density and making it work reliably at higher temperatures.
Lower power memory is always good. Sensors and actuators again.
Definitely. Magnetoelectric sensors for ultra-low magnetic fields think medical brain imaging without bulky cooling, or better navigation where GPS fails. And maybe even temperature sensors based on how their properties change. As actuators using piezoelectricity or magnetostriction for tiny, precise movements in nanorobots or precision optics.
So sensing the world and interacting with it. What about energy?
That's interesting too. Some research on using them for thermoelectrics converting waste heat into electricity via the Seebeck effect. Multiferroics might offer advantages there.
Okay.
And some, like BIFO, again, show a bulk photovoltaic effect. They can generate electricity from light without eating a PN junction like normal solar cells because their internal polarization helps separate the charge carriers, potentially higher efficiency.
Even generating power. Okay, quantum computing. Let's revisit that potential.
As we touched on, the idea is using their built-in state's ferroelectric domain direction, or magnetic moment orientation as the qubit's 0 or 1 state. The big potential advantage is electrical control. Using voltage to manipulate qubits could be much less energy-hungry than other methods. Plus, having both electric and magnetic handles could offer more control options.
But challenges remain.
Big ones. Decoherence is the enemy interaction with the environment, especially defects and heat, can destroy the quantum state very quickly.
Right. Keeping it quantum.
And figuring out how to actually wire these things up into a large-scale quantum processor, integrating them with other components, that's a huge material science and engineering challenge.
So exciting potential, but still needs breakthroughs. Looking forward, what are the main roadblocks and promising paths Shnepat sees?
Manufacturing is still a major hurdle. Making these complex structures perfectly, reliably, and on a large scale, really difficult. Minimizing those killer defects is paramount.
Scaling up is hard.
And ensuring they last long-term stability against temperature, humidity, stress, they can be quite sensitive.
But there's hope.
Definitely. He points strongly towards theory and computation helping out. using quantum mechanics, like density functional theory, DFT, to predict new materials and understand their coupling.
Designing them on computers first.
Exactly. And machine learning is starting to play a big role too, training algorithms on existing materials data to predict new candidates or optimize properties much faster than just trial and error in the lab.
Using AI to accelerate discovery.
Yeah.
Makes sense. So what's the ultimate vision here? Where could this lead?
Schneepat paints a picture of these materials becoming key components in future electronics, maybe in brain-inspired neuromorphic computing, definitely in ultra-low power memory, perhaps flexible devices, and of course potentially playing a critical role in making quantum computers and quantum sensors practical. But getting there needs chemists, physicists, engineers, all working together.
It really sounds like multiferroics are still, in many ways, just getting started. A field full of challenges, but also incredible potential.
Absolutely. And it's amazing how drilling down into the fundamental quantum interactions between electrons and atoms in a crystal can point towards solutions for such huge technological needs, like energy efficiency.
Indeed. So, to wrap up our quantum deep dives today, multiferroic materials. They possess multiple ferroic orders like ferroelectricity and ferromagnetism simultaneously. The really exciting part is the coupling between these orders, especially the magnetoelectric effect, which opens doors for entirely new technologies.
Yeah, from ultra-low power memories and highly sensitive sensors to potential roles in energy conversion and even quantum computing.
But, as Schneepat outlines, significant challenges remain, particularly in synthesis, defect control, and scaling up production. Still, advances in computational material design and ongoing research offer a very promising path forward.
It's a vibrant field, definitely.
All this insight drawn from the essay Multiferroische Materialien, Zukunft der Quantentechnologie by Jürgen Schneepat. Thanks for joining us on this deep dive.
My pleasure.
And we'll leave you with this to ponder. As we get better at designing and controlling these intricate materials, manipulating the dance between electricity and magnetism at the nanoscale, what completely unexpected applications might emerge? What new physics might we uncover along the way?